In today's video, I'm going to wrap up our chapter on solubility. So this is a very short unit. We just have 2 videos, and this one will cover sections 16.5, 16.6, and 16.8. So first, let's talk about what the solubility product constant is. So we call this KSP, and since it's a capital K, you might guess that it's an equilibrium constant, and you would be right. So KSP is just the equilibrium constant for a chemical equation representing the dissolution of an ionic compound. Okay, so that's basically you have a salt, and you dissolve it in water, and it separates into its ions, and that event has a dynamic equilibrium, like we talked a little bit in the last video, and so we can represent that quantitatively using an equilibrium constant, and we call that equilibrium constant KSP in this case. Okay, so the molar solubility is the solubility in units of moles per liter, and that just tells you how many moles per liter can you get to dissolve for a particular salt. Okay, so the first one that we're going to do here is silver chloride. So the KSP for the dissolution of silver chloride is 1.77 times 10 to the minus 10th, and it's asking us to find what the molar solubility is. So we're trying to find how many moles per liter of silver and chloride you can find in this solution when it dissolves in water. Okay, so first let's write out the equation. So AgCl, which is a solid, breaks down into Ag plus, which is aqueous, and chloride, Cl minus, which is aqueous. And the KSP for this equation is 1.77 times 10 to the minus 10th. So if we write that out, the KSP for this reaction is going to be equal to the concentration of silver times the concentration of chloride. And that's because those are our 2 products, and we don't have any reactant in our equation because it's a solid. And remember, solids do not go in our equilibrium expression. So if S is how much of it is going to dissolve, initially we don't have any dissolved, right? Because it's all in the solid form. And so our change is going to be plus S for both the concentration of the silver ion and the concentration of the chloride ion. So at equilibrium, that's how much will be dissolved. So this is just like the ice tables we've been doing. We're just using S because S represents the molar solubility, not just a change in the concentration. Okay, so in this case, KSP is equal to 1.77 times 10 to the minus 10th, and that's equal to S squared. So if we take the square root of both sides, we get S is equal to 1.33 times 10 to the minus 5th molar. And so that's the molar solubility of silver chloride. So they're very simple problems, and we're going to do a few of them, and you'll have a chance to practice them in mastering chemistry as well. Okay, here's another example, and this time we're trying to calculate the molar solubility of lead chloride, lead 2 chloride, and we can first write out the equation. So PbCl2 solid is going to dissolve to make Pb2 plus, which is aqueous, plus 2Cl minus ions, which are also aqueous. Okay, and we know the KSP for this is equal to the concentration of lead ion times the concentration of chloride ion squared, because we have a 2 next to it in our equation because there's 2 chloride ions. Okay, so when we write out our ice table for this one, it's going to look a little bit different than the last one. We're still going to start with 0 of each, and for each lead chloride that dissolves, we still get 1 lead ion, so that's just going to be plus S. But for each lead chloride that dissolves, we're going to end up with 2 chloride ions, so that's going to be plus 2S. Okay, so when we write out our KSP, it's going to be equal to S times 2S squared. So that's going to give us 4S cubed. All right, so to solve for this, we're going to have to take the cube root. If your calculator has a button that does that, that's great. If it doesn't, you can just do it to the 1/3 power using your little caret, and every calculator has that function. All right, so S is equal to the cube root of 1.17 times 10 to the minus 5th, because that's our KSP, divided by 4. All right, and if you calculate that out, you get 1.43 times 10 to the minus 2nd molar. So that's how much lead chloride will dissolve in water. All right, and then we can also go the opposite direction. So here we have a problem that's the molar solubility of silver sulfate in pure water is 1.2 times 10 to the minus 5th molar. calculate the KSP. So in this case, again, we are going to write out our equation, and then our expression for KSP is going to be the concentration of silver ion squared, because we have two of those, times the concentration of the sulfate ion. Okay, and then when we write out our ice table, it'll be plus 2s for the silver, because we have two of those each time we break one apart, and we just have plus s for the sulfate. So again, our KSP expression is going to be equal to 4s cubed, and you'll find that that's the case anytime you have an ion that's plus 2 or minus 2 with one that's plus 1 or minus 1. All right, and then KSP is going to be equal to 4 times 1.2 times 10 to the minus fifth cubed, and that's because 1.2 times 10 to the minus fifth is our S value in this case. So we're just going in the opposite direction to be able to find our KSP. All right, and when we multiply that out, you get 6.9 times 10 to the minus 15th as your KSP value. And remember, equilibrium constants do not have units, so that value doesn't have any units. All right, now I'm going to talk about something called the common ion effect. So in general, the solubility of an ionic compound is lower in a solution that contains a common ion than it is in pure water. And what this means is that if we already have some of the ions present, not as much of the salt is going to dissolve. Okay, so let's look at this mathematically, so hopefully that will help you make some sense of it. So what's the molar solubility of CaF2 in a solution that contains 0.1 molar NaF? So CaF2 is going to break apart into Ca2 plus 2F minus. And I'm not going to write it out, but hopefully you can see that the NaF would also break apart into Na plus and F minus. And it's going to do that almost completely because it's got that sodium ion there, which we know is pretty much always soluble. Okay, so when we do our ice table for this particular reaction, we'll have 0 as our starting concentration for calcium, but our starting concentration for fluoride is going to be 0.100, and that's because we already have some fluoride ion present in the solution. So our change is going to be the same. We're going to have one calcium ion form for each one that dissolves and 2 fluoride, so it'll be plus S and plus 2S, which gives us equilibrium concentrations of S for the calcium and 0.1 plus 2S for the fluoride. Okay, and this is not a very soluble salt to begin with, and since we already have the 0.1 for the fluoride, S is going to be relatively small compared to that, so we can ignore it. Okay, just like we did in the problems in the previous chapter. Okay, so this gives us KSP is equal to the concentration of calcium times the concentration of fluoride squared, which is going to be S times 0.1 squared after we cancel out the plus 2S. Okay, so if we solve, we know that KSP is equal to 1.46 times 10 to the minus 10th. If we divide that by 0.1 squared, then we end up with S being equal to 1.46 times 10 to the minus 8th molar. Okay, so having that additional fluoride ion in there makes almost none of the calcium fluoride dissolve. 1 times 10 to the minus 8th is a really, really small concentration. All right, so now we've talked about how things will dissolve. So let's talk about what happens when they come back out of solution, which is called precipitation. All right, so we're going to go back to the idea of Q, which is what we could calculate for our equilibrium expression if we put it in our initial concentrations, but this is not equal to the salt at equilibrium. So we're looking at how Q compares to KSP can tell us whether the solution is unsaturated, saturated, or supersaturated. So as a reminder, unsaturated means that more solute could still dissolve. So in that case, we could have more ions dissolved in solution, so that expression could get bigger. So that means Q must be smaller than or less than KSP in this case. All right. If it's saturated, we have exactly the right amount of solute dissolved, which means that Q is going to be equal to KSP in a saturated solution. And then remember we talked about supersaturated solutions, are very unstable and don't happen all that often, and usually just a small perturbation can cause the excess solute to come back out of solution. So in this case, Q is actually greater than KSP, but remember that this is a very unstable situation. So here is an illustration just to remind you of what the saturated, unsaturated, and supersaturated look like, but we did talk about them in the last video as well. So the last thing we're going to talk about in this unit is complex ion equilibria. And these are just a little bit different than the equilibria we've talked about already. They look kind of like ionic compounds, but they're slightly different. So a complex ion, it consists of a central metal ion that's bound to one or more ligands. Okay, so an example of a complex ion, because it's a little easier to explain this way, is AgNH3 2+. So in this particular example, the central metal ion is the silver, and the ligand is the ammonia, okay? So ammonia doesn't have a charge in this case, but it could be something that has a charge. And there are two of them that are bound to the central metal ion, and it has the same charge as all the charges added up. So silver ion has a +1 charge, the ammonia is neutral, and so the complex ion has a +1 charge, okay? And then, so just as a review, the ligand is either the neutral molecule or the ion that is binding to the central metal ion. Okay, and then the formation constant, or Kf, is just the equilibrium constant for that formation. So if we write out the formation of the example I just gave you, it's Ag plus 2NH3 goes to AgNH3 2+. Okay, that's a pretty simple equation. I'm not going to expect that you remember the complex ions, and you shouldn't need to know them for the AP exam, but if I were to give you an ion, you should be able to write out the equation that gets you that complex ion, right? Because it's just the central metal plus the whatever ligands are there. Okay, and then for that particular one, the Kf value is 1.7 times 10 to the minus 7th. All right, and if we wanted to write out that that value mathematically, it would be Kf is equal to the concentration of the complex ion, because that's our product, divided by the concentration of the metal ion times the concentration of the ligand. And in this case, we had two of them, so it's the ligand squared. Okay, so now let's do an example of this. So this is a fairly complicated example, but I wanted to take you through one that would have all of the steps that you might potentially need to do. So you mix a 200 milliliter sample of a solution that is 1.5 times 10 to the minus 3rd molar, I apologize, there's a typo there, in copper nitrate, okay, with a 250 milliliter sample of a solution that is 0.2 molar in NH3. Okay, after the solution reaches equilibrium, what concentration of Cu2 plus remains? Okay, so basically what this is asking, we have copper nitrate. You know that's going to dissolve completely because it's got nitrate in it, which is one of the 4 ions that always dissolves. Okay, and so we could calculate how much copper is in solution when we're starting. And then you add ammonia to it, the NH3, and that is acting as our ligand. Okay, so if I were to give you this problem on a test or in the homework or something, you would need to find out what complex ion forms from that. And I won't expect you to remember it or to be able to figure that out on your own. But the complex ion that forms is CuNH3 2+. All right, so again, NH3 is neutral. Copper has a 2+ charge in this compound, this ionic compound that we have. And so that's the overall charge that you'll get for the complex ion. And the Kf value for that is 1.7 times 10 to the minus 13th. All right, so the first thing that we need to do is figure out how much of each of the ions, or how much of the metal ion and the ligand we have in solution to start, and then we'll do an ice table to figure out what the equilibrium concentration is. Okay, so the initial Cu2 plus concentration is going to be the 0.2 liters, because that's how much of it we have, times the concentration, which is 1.5 times 10 to the minus 3. Okay. And then we'll have to divide by the total volume since we're adding 2 solutions together. So that's 200 plus 250 milliliters is 450 milliliters. All right, and so that gives us an initial concentration for that of 6.7 times 10 to the minus 4th molar when you multiply out and divide all that out. And then for the NH3, again, we'll have the same volume on the bottom, the two volumes added together. And on the top, it'll be 0.25 liters times 0.2 over 1, because that's how many moles per liter we started with. Okay, so that'll be 0.11 molar. So now if we make our ice table, our initial concentration is going to be 6.7 times 10 to the minus fourth for copper and 0.11 for the ammonia. And our complex ion has an initial concentration of 0 because we don't have any of that to start. Okay, so what we are looking for here is the concentration of copper at equilibrium. And so that is actually what we're going to set to our x in this problem, which is a little different than what we've done before. And the reason we're going to do that is because you can tell from the fact that the equilibrium constant, the formation constant for this complex ion is humongous. It's 10 to the 13th. That's a really, really big number. And we already have a lot more NH3 in our solution than we have copper. So almost all of it is going to disappear, but not quite. Okay, but it's going to be enough that we can approximate that as our change. Okay, so the approximate change of copper is going to be 6.7 times 10 to the minus fourth, even though we know there's going to be a little bit left. And we can go back after we calculate our number and double check that this makes sense. All right, and then for the ammonia, it's going to be minus 4 times 6.7 times 10 to the minus fourth, because we need 4 of those for each complex ion. And then our increase in concentration for the complex ion is going to be about 6.7 times 10 to the minus fourth, right? Because that's the maximum amount we could make if we use up all of the copper, right? So now our Kf is equal to the concentration of our complex ion divided by the concentration of copper times the concentration of ammonia to the fourth, right? So when we plug all of our values in for equilibrium, we get 6.7 times 10 to the minus fourth divided by x times 0.11 to the fourth, all right? Because if we subtract 6.7 times 10 to the minus fourth from 0.11, we get the same number, right? Because to minus 4 is pretty small. Okay, so this just makes our math a little bit easier. So if we multiply that out and solve for x, we get 2.7 times 10 to the minus 13th. Okay, so it's a really small amount of copper that's left, and you can see that from the perspective of how much we used, our approximation is valid. Now I understand this is the most difficult thing we're doing in this unit, and it'll take a little bit of getting used to, but also keep in perspective that you might have one of these problems on the AP test, but in the last couple years I've never seen one. But I felt like it was important to expose you to what a complex ion was and how you would do these calculations. But all of the logic that we're using in this problem is similar to what we've done in this chapter with equilibrium in acids and bases and what we did with general equilibria earlier on. Okay, so bear with me. We'll do a little bit of practice with this, and hopefully it will become a little bit more comfortable.